Okay, let's see how you're doing on these so far. So we're going to look at number one over here, which is just, it's a prism with a base that is a trapezoid. Now that's not a word we necessarily covered, and it's not an area that we calculated, but it isn't one that's hard to figure out. So we're going to look at the base of this as a trapezoid. I'm actually going to flip it over, if my pen will work. And draw it like this. Maybe. Okay. Now, this trapezoid is 8 units on top, 8 inches on top, 20 on bottom, and it is 10 going this way. So for volume, the first thing we have to find is the area of a base. I'm going to do it by cutting it like this. So what I have now is piece 1 here that is a rectangle that is 8 inches by 10 inches. Which is 80 square inches. Piece 2 is going to be found by putting together these two triangles. If I put them together, I know this height is still 10 inches. What's the base down here? 12. Very good. 20 minus 8. If there's 8 on top, that takes 8 out of here. That means there's 12 left over. So that second piece is a triangle that is 12 inches by 10 inches. But since it's a triangle, its area is divided by 2. Remember, a triangle is base times height divided by 2. Giving us 60 square inches. So that adds up to an area of our base of 140 square inches. So our volume is found by taking the area of that base, 140 square inches, times the height, which is 20 inches, which is 2,800 cubic inches. For surface area, we have the area of the bases as 140. And there are 2 of them. There's one on top, one on bottom. So what we still need to find is the lateral area, which is the area connecting the bases. To find the lateral area, we need to know the perimeter of the base. To find the perimeter of the base, we need to know some missing sides. So if this is 8 and 20, and this is not going to write, that's 10. Oh, heck no. They've been trying to get it away from me for 3 years. And that's 10. What we need to find is the length of these sides here. Well, what we're going to do, now I have to make an assumption here because without the assumption, there's nothing we can do. We have to make the assumption that these two ends are the same. So this is 6. Half of that difference is 12. So if that's 6 and this is 10 here, 6 and 10, that's a right angle. Well, then we have to use our a squared plus b squared equals c squared to find the missing side. Remember, that only applies to a right triangle. Well, we have this right angle right here. So we know it's a right triangle. A and B are the sides that make the right angle. So these are sides A and B. C is the side that's across from the right angle. It's the longest side. So it's a squared plus b squared equals c squared. So a is going to be 10, so that's 10 squared. Plus b is going to be 6, so that'd be 6 squared. Equals c squared. So 10 squared is 100. 6 squared is 36. So it's 136 equals c squared. So we have to square root. So we have to use our square root key on our calculator. Square root of 136 is going to be 11.66. So this side is 11.66 on each side. So the perimeter of our base is 8 plus 11.66 plus 20 plus 11.66, which is 51.32 inches, correct? Okay, good. So then our lateral area is that perimeter of the base times the height of 20 inches. So that's going to come out to be 1026.4. And that is inches squared. So I add that up with the 240s, and I get 1306.4 square inches. That is my total surface area. So volume, 2,800 cubic inches. Surface area, 1,306.4 square inches. Okay, now over to number 2. Number 2 is mostly a matter of seeing what the pieces are that fit together here. And we have 3 pieces. We have a cone, number 1. Number 2 is a cylinder laying on its side. And number 3 is half a sphere. So for volume, we're going to need to find the area of a base for the cone and the cylinder. And both of those have the same base. It's this circle right here. What do we know about that circle? We need to know either a radius or a diameter. What'd you say? Well, no, actually, the 8 inches goes with the cone. How do you get 6 inches on it for a radius? Okay. This is a tricky one because the length from here all the way out to here is 26, and from here to here is only 20. That tells us the distance from here to here is 6. So that must be the radius of our half sphere out here. And that radius goes in every direction. So that would also be 6 inches going straight up. So that would be the radius of the cylinder and of our cone. That was tricky just to find that. Once you have that, then the area of that base, the area of that circle, is pi times 6 squared, otherwise known as 113.404. Thank you. And that's going to be, oops, I said inches there, but it's actually feet squared. That should have been feet and feet. So 113.04 square feet, the area of that base. Now I can find the volume for my individual pieces. For number 1, for the cone, that volume is the area of the base, the 113.04 square feet, times the height of 8 feet divided by 3. Yep, 301.44. Cubic feet. Number 2 is a cylinder. The volume of that cylinder is the area of the base, 113.04 square feet, times its height of 20 feet. (2,260.8) cubic feet. And finally, piece 3. That ain't going to show up very well. Which is the half sphere with a radius of 6. Remember, the volume of a sphere is 4/3 times pi times radius, which is 6 in this case, cubed. But it's only half a sphere, so we're going to divide that by 2. So 4 divided by 3 times 3 times 3. 0.14 times 6 cubed divided by 2. 61.53. cubic feet. So we add that up, we've got 2,622.05 cubic feet. That's our volume. For surface area, the area of the bases do not come into play here because all of the bases are covered with other objects. The base on the cone here is covered with the cylinder. The base on this end of the cylinder is covered with the cone. On the other end of the cylinder is covered with the half sphere. So it's all lateral areas and then the area of the half of the sphere. We still need to find the perimeter of the base, which is the perimeter of that circle, which is just going to be pi times 12. Which is 37.68 feet. Correct? Okay. So then our lateral area for the cone. Requires us to have that perimeter of the base times the slant height. We don't know the slant height yet, do we? And of course, we'll divide that by 2. Our slant height is found off of this triangle here. That triangle is going to be 8 here, that's the height of the cone, and 6 here, which is the radius of that circle. So what I'm finding is the hypotenuse of a triangle with legs of 6 feet and 8 feet. So this is A, B, and C. C is the side we're looking for. So A squared is going to be 8 squared, plus B squared will be 6 squared, equals C squared. So that's 64. 6 squared is 36. 64 and 36 makes 100. C squared equals 100, so then we must square root it. Square root of 100 is 10. So that's our slant. So that gives us 184. Thank you. 188.4. square feet. That's off the cone. Off the cylinder. The lateral area is the perimeter of that base. $37.68 times the height of 20 feet, which ends up being yes, 753.6 square feet. And then finally, the lateral area for half a sphere well, surface area for a sphere is 4 times pi times radius squared, and of course we're going to have to divide that by 2. Gives us 226.08. So we have to add those all together to give us 1,168.08 square feet is our surface area. Now, to ease your mind a little bit, I would never give you problems that difficult on a test. I just chose those two problems because that basically, those two problems contain everything I would ever expect you to know about volumes and surface areas. Any questions? That's just the warm-up for the day. So now, I hear that a lot. I'm a math teacher. That means I'm not a very nice person, right? We talked a lot yesterday about the introduction to statistics and sampling and stuff like that, and how incredibly important it is to take what we call a representative sample. And what that meant was the sample statistics remember the sample statistics. A statistic is a piece of information that describes an element of interest of the sample. Now, I'm not saying, there's 40 people in the sample or anything like that. Those are not statistics. That's defining the sample. Describing the sample is talking about what it is that we're trying to learn about, that variable of interest, that question. We want to know, how much do you, as students, spend on books at WITC? Well, we took a sample and we find out your price of books and we find an average. That would be our sample statistic. And we're going to compare that to a population parameter. A parameter is very similar to a statistic, only it describes the whole population rather than just the sample. Now, most of the time, we have no clue what the population parameter is. That's our reason for taking a sample and calculating its statistic. We're trying to use that sample statistic to predict or to estimate the population parameter. So a representative sample, that sample statistic will be equal to or really, really close to being equal to the population parameters. Now, we'll never really know for sure because if we knew the population parameter, we'd have no reason to take a sample. So a sample statistic might be saying, of the 40 students we surveyed, the average cost of books was $482 a semester. That's a sample statistic. A population parameter is a little bit tricky because we generally don't know the exact numbers. So we might say, based on our information, we estimate that the average student at WITC spends around $500 per semester on books. That's not an exact number, but it is being used to describe the population. We're saying that every student at WITC spends around that much on average on books. And if that sample, like I said, is a good sample, that sample statistics will be a good estimate of the population parameter. It'll come out really close. And the ways to make that a representative sample was to have an adequate sample size. I can't just sample 2 students and say, oh, on average those 2 students together. That's not a good sample. And second, sample selection. I have to be very careful to select a sample at random. Remember, random means everybody in the population has an equal chance of being in that sample. And we talked yesterday about different methods that were random for sampling. But remember, the best one was the simple random, which meant you just threw everybody's name in a hat and drew them out. And those were the ones that were in your sample. The problem, of course, with simple random, even though simple random is the best, and statistically it's the one that fits our calculations and processes the best, it can be tedious to do. Sometimes the other ones are just way easier to do and more cost effective. So in reality, we often substitute those other samples for a simple random sample. So we're not going to talk about that anymore. As you might guess, it's really hard to ask a test question on any of those anyway. I'm not going to, ask you on a test, define what a cluster sample is or anything like that. That vocabulary is just out there so that you understand when I say something, what those words mean. What we are going to be testing on, what we are going to be hopefully pulling out of this mathematically, is a little bit of knowledge of distributions. And we talked distributions a little bit yesterday. We talked about that dot plot. And that dot plot is just a number line that encompasses the range of the data. Now, let's say that let's do the textbooks. And let's say that we have textbooks that a student that went as low as $180. And as high as just under $500. So we take what they spent on textbooks and we put it on this dot plot. So let's say we surveyed one student and they spent $380. That goes right there. Another student spent $260. There's a dot there. Another one was $320. Another one was $340. Another one was $210. Another one was $420. $300. $320 again. And we keep surveying students, calculating the amount they spend on textbooks, and adding those dots to our plot. And what we see is this plot starts to take on a definite shape. And if we plot enough of those points, we can come through and then trace through the top dot in each spot, and we can get a curve. That curve is the distribution. Many times, in fact, most of the time, you might recognize the shape of this curve as what we call a bell curve. The technical name for that is a normal curve or normal distribution. And the reason it's called a normal distribution is because that is the shape that most numerical things in nature normally take. Heights of people, weights of people, income, average income, stuff like that will take that shape. A good, well-written test, the scores on a test will look like that if enough people take it. Now, the biggest thing is you can't just do 4 or 5 people and plot them and get a normal distribution. It takes a lot of people, quite a few people, to get that shape to work out. So as we look to describe this distribution, yesterday we made all the graphs and tables and stuff. We described the data graphically. If we are going to describe or summarize data numerically, we need to describe this curve with numbers. And one of the things about this curve we can describe is its center. The peak of that bell is the center of the curve. So imagine this is my number line again. And this blue curve is our set of data. I find another set of data. It looks like this. The difference is the center of the blue curve is right here. The center of the brown curve is up here. The curves have the same width. Their center is moved. The center of the brown curve is what we call higher because these are the larger numbers as we move to the right. Smaller numbers would be as we move to the left. So the center of the brown curve is larger than the center of the blue curve. We could have a bell curve like this green one. Now the center of that curve looks to be the same as the center of the blue curve. How would you describe the difference between the blue and the green curve? Well, the green curve, I would say, is more spread out. So that's the second thing we need to describe about them is spread. There's a third thing that we're not going to talk a lot about called skewness. The skewness just means that curve may not be a perfect bell. A skewed bell leans a little bit one way or the other. I exaggerated these a little bit, but this one here would be called skewed left. This one would be called skewed to the right. The ends of this are called tails. The ends of that curve. If it's skewed left, the left tail is stretched out. If it's skewed right, the right tail is stretched out compared to your standard symmetrical bell. Skewness is sometimes also symmetry as well. So let's talk about measures of center. To do this, I'm going to give us a simple set of numbers to work with. 17, 11, 21, 15, 29 is our set of numbers. So our first thing we need to look at is the mean. The mean is what most, oops, the picture disappeared. Okay, so hopefully that fixes that problem for a while. The mean is just the average. It's that same average that we learned back in about third or fourth grade of adding the numbers up and dividing by how many are there. Now, one of the things we're going to look at, n, is the symbol for the number of items in a list. And we're going to say number of items in a sample is what we're going to call it. The symbol looks like kind of a funny E. That is a capital Greek sigma. And that means sum or add up. So the symbol for mean is the Greek letter mu, the same as our symbol for micro, if it's a population. It is x bar, x with a little bar over it, if it's a sample. The formula is the same either way. That sigma sum, and then the x means add up all the values and divide by how many are there. So in other words, I'm going to add up. 17 plus 11 is 28, plus 21 is 49, plus 15 is 64, plus 29 is 93, divided by 5. And that does come out to be 18.6. So 18.6 is the mean of this set of data. The second measure of center is something called the median. The median is literally the middle number in a set. To find the median, there's actually a couple of steps you got to go through. Step 1 is find the position of the median. And actually, there should be another step 1. I'm going to take that out. Find the position. There's an assumption made there. Step 1 should put the data in order. So over my list here, those are not put in order. So the first thing I would have to do is put them in order from smallest to largest. Now, many data sets I'm going to use are already going to be put in order. So step one will be done for us. Step two then is to find the position of the median. The position of the median is going to be found by taking 0.5 or 1/2 times n. Remember the 1/2, the median being in the middle, that means there's a half of the data on either side of the middle. So 1/2 times n, which in this case is going to be 1/2 times, what's n here? What's n? 5. There are 5 numbers on the list. So that's 2.5. Since that is a decimal, a 0.5, we round up. So the median will be the third number in the list. So then our final step is to find the median in the list. So 1, 2, 3, 4, 5. The third number is the 17. That's our median. Now, some of you may have been taught to do a median by just starting at the ends and crossing off the ends and work your way into the middle. That works great on a set of numbers like this. It's only like 5 or 6 numbers. If you have like 200 numbers, that could take a while. Now here, this was an odd set of data. What I mean by that is n was odd. What if n is even? Let's do this again for a new set of data. Now I'm going to skip step 1 and I'm just going to put them in order right away. So for this set of data, what's n equal? 6. So step 2, finding my position. It's going to be 1/2 times 6, which is 3. Since that position I calculated is a whole number, that means the median is between that position and the next. So up here, when it was a decimal, it was just rounded it up, and that's the position it was in. When it came out to be a whole number, it's between that position and the next. So my position here, 1, 2, 3, 4, 5, 6. It's between the third and fourth. So it's between 18 and 19. How do we find out what's between them? Exactly. Add them together and divide by 2. That's 18.5. That is our median. The final measure of center, I shouldn't say final, there's a couple other ones we might look at. The final one of what's usually called the big 3 measures of center is the mode. Mode is the item in the list that appears the most often. Now, in my list of numbers here, none of my lists had a number that appeared more than once. So none of them had a mode. While a mode can be used in numerical data, it's not terribly useful in numerical data. A mode is usually used for categorical data. Like the other day, we talked about favorite color. Well, the mode would be the color that was chosen the most often. And the only reason the mode is useful is because with categorical data, you can't find a mean or a median because there's no numbers to work with. You can find a mode in numerical data as well. These here, however, would be no mode because no number appears more than once in either one of them. Now I talked about, well, let's talk about this next one first. There's a fourth one. Like I said, the mean, median, and mode are the big three. Those are the three that are used all the time. There are some other ones. I'm going to bring up one called the mid-range. The mid-range involves two numbers. One is called the max, or the maximum. That's the largest number in the set. If I look up here, largest number in this set is the 31. And the minimum, which is the smallest number in a set. If I look up here, the smallest number in this set is the 7. The mid-range is found by averaging those two together. Add them together and divide by 2. Now, very important little side note for you. If you're doing this on the calculator, you do 31 plus 7, press equals before you press divided by 2. If you do 31 plus 7 divided by 2 without hitting equals, it'll tell you it's 34.5. Well, what it does is division, in order of operations, division happens before addition. So it's just going to divide the 7 by 2 and then add it to the 31. So you want to do 31 plus 7, hit equals, and then divide, which is going to give you 19. Is our mid-range. If our distribution is perfectly normal, in other words, symmetrical, pretend that looks symmetrical. In our bell curve, the mode, of course, is just the highest part of the curve. That's the value that occurs most often. The mean should be the same value. And the median, also the same value. So in a good set of data, a perfectly normal set of data, the mean, median, and mode will be the same value. That's one of the ways we test to see if a set of data is normally distributed, is we find the mean, median, and mode, and if they're the same value or really close to the same value, chances are that's data that is normally distributed. If it's skewed left, the mode, of course, is still the highest part of the curve. The median, depending on how skewed it is moved a little bit. And the mean is moved a little bit further depending on how skewed it is. So the mean and the median both get pulled in the direction of the skew. If it's skewed right, well, you might be guessing that it looks just the opposite, and you'd be correct. The mode is still the highest point of the curve. Median is moved a little bit, and the mean moves a little bit more. So now, the age-old argument. What is the best measure of center? Now, I told you flat out, the mode is really only useful for categorical data. For numerical data, there is a mode, but we usually don't care about it, don't care for it. So it comes down to really the mean and the median. Which one do you think is the best measure of center, the mean or the median? Yeah, usually I get a few people will say median, but most people will say mean. And it's probably because it's comfortable. I mean, most of us learned how to find an average in 3rd or 4th grade. And there's something comforting about cranking out a formula, adding them together, and dividing by how many are there. But I'm going to give you an example. Yesterday we talked a little bit about how some of those graphs can be used to be deceiving, especially the bar graph, so they can change the width of the bars, cut out parts of the scale on the axis to accentuate differences and stuff like that. I'm going to use this example. It's 1983. The University of Virginia said that an average starting salary of a bachelor's degree in marketing for a graduate from their university in 1983 was about $78,000 per year. Now, let me put this in perspective. In 1983, your average high school teacher had a starting salary between $16,000 and $18,000 a year. $78,000 a year was a very good starting. Now it would be a good starting salary. If you offered me that right now, I might not be here tomorrow. That's a good starting salary. No, I'm not going to leave. You guys wouldn't get that lucky. Sorry. The 60,000 would work. Yeah, I mean, the 16 or 18 would be good right now. Yeah, I hear you. That was a very good starting salary. Well, what they failed to disclose, that was an accurate number, by the way. That was the average mean. What they failed to disclose was one of the graduates in 1983 was a man by the name of Ralph Sampson. Ralph Sampson was 7 feet 4 inches tall. It was the 2-time NCAA Basketball Player of the Year. Was drafted number 1 by the Houston Rockets. Yeah, made a few million that year. But he did graduate in the marketing program. He did graduate in the Bachelor's Degree Marketing program, so it's counted. Now, the people that graduated with a bachelor's degree in a marketing program and were still a cashier at a gas station still counted. But they were graduates. Yeah, it skewed the distribution a bit. It takes a lot of $20,000 a year marketing graduates to average one multi-million-dollar contract to $78,000 a year. He was the only person in the group to earn over $33,000 that year. That was the mean. Was the 78,000. The median was 24,000. The two terms that get used here are resistant or sensitive. And it all depends on what textbook you're looking at and what direction you're looking at it from. Resistant means not affected by what's called extreme values or outliers. Mr. Sampson's multi-million dollars was an outlier. It was way away from the other values. It affected the mean way more than it affected the median. The median was more resistant to that outlier. The mean was more sensitive. So yes, in general, we tend to accept the median as being a better measure of center than the mean, because the median is less sensitive and more resistant to those outliers. One outrageous value isn't going to drastically change the median. For example, let's say I give you a set of numbers. I'm going to have you guys do some calculations here. I am going to put these in order from smallest to largest just to make life easier on us. Find for each of those sets of data the mean and the median. So for the first one here, the mean is 18 and the median is 16. So that's telling us, by the way, is that this data set is already slightly skewed. If the mean is bigger than the median, it's slightly skewed to the right. Yes. Oh, yeah, sorry. I thought you had your hand up. So it is already slightly skewed. For the second one here, the mean is 25 and the median 18. That's extremely skewed. And of course, it would make sense that it's more skewed because we added that really large number of 60, which isn't even terribly huge, but you can see it changed the mean by 7. The median only changed by 2. So the median was less sensitive. The mean was more sensitive. And the median was more resistant. Well, the mean was less resistant to that large number. Again, that is what we call an outlier. I spelled that way wrong. Let me try that again. There, outlier. And there are a lot of different ways of defining outliers. Outliers can be defined as on the top end, more than double the next value. 60 is more than double 27. Now on the bottom end, that doesn't work so well. That definition does not work. So that's only for an upper outlier. We haven't talked about standard deviations yet, but more than 3 standard deviations from the mean. And we haven't talked about quartiles yet, but more than 1.5 interquartile ranges from a quartile. Now in this class, there's 3 ways of identifying there. In this class, we will not be asked to identify outliers formally like this, but it's something that's out there that's, if you get into more data analysis, it's very important. Outliers must be identified and they must be analyzed. Because when you see an outlier, you have to ask, is this a real value or is it a mistake? Sometimes outliers are just real values that just happen to be unusual, like Ralph Sampson making way more than any other graduate in that program. Sometimes it's a mistake. Sometimes you wrote a number down wrong, got an extra 0, or misplaced a decimal point, or the decimal point didn't show up. Or measurement error, or something like that. Something went wrong. Okay, we're a little bit early, but let's take our break here. It is 10:09. Let's shoot for about 10:19 or 10:20 to come back and talk about measures of spread.